Okay, so we're going to talk about the last unit of GHS chemistry this year. And the first lesson in that unit is properties of acids and bases, and a little bit of understanding of what pH actually is. So in today's lesson, we're going to start by talking about some basic definitions. One of the basic definitions that we need to talk about is what is an acid. And so in this case, there's two definitions of an acid that you're going to have to be familiar with. The first definition is something that we call an Arrhenius definition or an Arrhenius acid. The other one is called a Bronsted-Lowry definition or Bronsted-Lowry acid. Now, in all of chemistry, there's still one more definition of acid that's out there, but we're not going to cover that in the scope of this class. So, in Arrhenius acid, talks about the release of H plus in water to form H3O plus. But before we talk about that, I want to talk about what H plus actually is. Hydrogen, as you might recall, if we look at the number of protons, neutrons, and electrons for hydrogen, hydrogen has an atomic number of 1, so that means that it has 1 proton. And in a neutral atom, that means it would have 1 electron. And hydrogen has a mass number of 1 also. So if you take the atomic number minus the mass number, hydrogen's number of neutrons is 0. Okay? So a neutral atom of hydrogen has 1 proton and 1 electron, and that is all. So the nucleus is simply a proton, and the electron is orbiting outside the nucleus. When a hydrogen becomes an ion, it becomes a +1 ion. And I've told you in the past that hydrogen sometimes behaves as a metal, and it kind of does, because protons still going to be 1. Neutrons, still going to be 0. However, when an atom loses an electron and gets a positive charge, it now, in this case, will have no electrons either. So a hydrogen atom can sometimes be referred to by chemists as simply a proton. So when we have a hydrogen ion, we sometimes refer to it simply as a proton. And so any substance that is added to water that adds more hydrogen ions to water is something that we call an Arrhenius acid. And when it's added to water, what's actually happening is a water molecule will snatch up that hydrogen ion to form the H3O plus ion that we call hydronium. Okay, so that's the H3O plus ion. So when we do this, or when that happens, we're simply adding more hydrogen ion to solution. Now, I want to but I want to take a second to talk about like water for like a hot second. We've always written water as like H2O, but in this unit, sometimes water can be written as HOH. And actually, it can always be written as HOH because it's still H2O, but it's now looking at the fact that we're looking at hydrogen ion, and we're going to talk a little bit more about hydroxide ion in solution. So in Arrhenius definition, another way to write the Arrhenius definition would be anything that increases the amount of hydrogen ion in solution. Now, the Bronsted-Lowry definition is very similar, but it's not exactly the same. So in this case, it says a Bronsted-Lowry definition is a substance that donates a hydrogen ion to another substance. It's sometimes referred to as a proton donor. It just basically is a substance that transfers or gives a hydrogen ion somewhere else. So in my example down below where I have hydrochloric acid, which is HCl, and I have neutral water, what ends up happening is the hydrogen ion that's in HCl, and HCl technically has 1 minus. Chlorine does anyway. So that hydrogen ion gets transferred to the water to make H3O plus. And when it does that, we now have aqueous H3O plus and aqueous chlorine ion floating around in solution. So going back to the two definitions up above, an Arrhenius acid is anything that adds hydrogen to your solution. A Bronsted-Lowry acid is anything that transfers hydrogen to something else. So in this case, the hydrogen was transferred to water, and now we have H3O plus. Okay. All acids have some similar properties. Acids will react to neutralize bases. So if I told you that an acid like HCl reacts with a base like NaOH, and hopefully you can identify this to be a sort of double replacement reaction, what you might think is going to happen here is we're going to make HOH and NaCl. Okay. Now, if this is aqueous and this is aqueous, this will be a pure liquid of water. Okay. And this will also be aqueous. Now, what that means in terms of acids will react to neutralize bases is that hydrochloric acid will react with sodium hydroxide to, in theory, make pure water and some salt. And I know what some of you are thinking. Some of you are thinking, wait a minute. What you're saying here is that if I take an acid and I pour it in my mouth and I take some base and I pour it in my mouth, I can swallow it and I'll be fine. And the answer to that question is no, you can't. That's just stupid. That's not even science. That's just dumb. Okay. Now, acids will also change the color of acid-base indicators, and I'll show you an example of that in a minute. Acids all have a sour taste. Now, we don't taste anything in the lab ever. Like, that's not allowed. But like at some point, somebody had to taste an acid to determine that it tasted sour. You probably have all eaten something that has had acid in it in your lifetime.
I was going to say, I saw this thing where like there's this one certain kind of acid where you like that they use to make like Sour Patch Kids or something, and you can add it to anything, and it makes it taste like a sour candy.
Yes. And we're going to talk about that in a second. You beat me to it. But yes, you're right. Acids have a sour taste, and common foods that you can eat that have acid in them are things like your lemons, your limes, your oranges. Okay. Acids produce, and I'll come back to your statement about the Sour Patch Kids. Acids produce H2 when reacted with active metals. So an example of an active metal might be something like zinc reacting with hydrochloric acid. That will produce the product, which this is aqueous, and this is going to be solid. Okay, so that'll produce zinc chloride. Okay, and it's going to also produce hydrogen gas. And I realize that I'm not balancing these because I'm just trying to maybe I will balance it in a second here. But the point that I'm trying to make is if I take a metal like zinc or magnesium, right, and I pour hydrochloric acid on it, it starts to bubble. And that bubbling is an indication that gas is formed. Let's see, I should probably throw a 2 here, and I think that balances it to make everybody feel a little bit better. Now, acids also have a value where the pH is less than 7, and we haven't actually talked about pH yet. So I'm going to say that anything that's in a range of 0 to, like, say, 6.9er is considered to be an acid. We'll talk about pH momentarily. All right. So those are properties that acids have, and you do need to know those. So what are some common acids? Sulfuric acid in its raw natural form is scary acid. I don't like working with it. It's very sketchy. But it's commonly found in batteries. Like your Duracell batteries have it in them, but it's more like a paste. In a car battery or a motorcycle battery, when you buy that battery, it comes, well, maybe not the car battery, but when you buy like a motorcycle battery or a lawnmower battery, it comes with this little teeny tiny container of a clear solution. And that clear solution you pour into the holes of the battery itself. And what that solution is actually sulfuric acid. And what that solution does is it's part of the reaction that allows the battery to work. So sulfuric acid is commonly found in batteries. Nitric acid, also a super scary acid in my opinion by itself, is used to make fertilizer. Hydrochloric acid, that's your tummy acid. So it's inside your stomach. You might be familiar with hydrochloric acid. Like, have you ever had like a rotavirus where you threw up all the time and then like your throat feels burny after you throw up? That burny feeling after you throw up isn't like your food coming back up. It's the acid in your stomach coming back up and like burning the cells of your esophagus. So you're having a little minor chemical burn inside your throat when you throw up. Gross. Okay. Citric acid, found in lemons, limes, and citrus fruits. You can buy powdered citric acid and just like add it to stuff, and it'll taste like fruity. Okay. Phosphoric acid is also like it's one of the acids in the Mountain Dew, but it's an acid that definitely gives the Mountain Dew its distinct taste. And then vinegar itself is found, or is basically a solution of watered down acid. So those are some common examples of acid that you might have run across in your daily life. Any questions about types of acid? Yeah, so citric acid and or phosphoric acid, both you can find them as a powder. You can generally, citric acid is the more safer one, the less sketchy one. And when you do add it to foods, it definitely tastes citrusy or tangy. Okay, so there's that. All right, now, bases. There's two different definitions of bases you should be familiar with. There's the Arrhenius definition and the Bronsted-Lowry definition. Now, an Arrhenius definition of a base is anything that you add to a solution that increases the OH concentration in water or hydroxide. Okay. So if you look down below, you see NaOH. You add that to the water, and you get sodium in its aqueous form, and you get hydroxide in its aqueous form. Now, I should have done this before, but like if I have a container like this, and in a container like this, if I write it kind of like and I write it like this, okay, so I've got water, right? If I go ahead and I add something like NaOH to it, okay, on my product side, I'm going to have my still 3 particles of water. But I'm also going to have another OH just kind of floating around. So I've increased the amount of hydroxide in solution by adding something to that. So in Arrhenius definition, another way to put it is any substance that increases the amount of OH or hydroxide in solution. Okay. Now, the Bronsted-Lowry definition is a substance that accepts a hydrogen from another. So this is sometimes referred to as a proton acceptor. Okay. So that's sometimes referred to as a proton acceptor. And here's where things are going to get a little bit different. So if I did the formula that was up above, it was like HCl plus H2O, and then it made the Cl minus 1, and then it made the H3O plus, right? Do you remember that from before? Okay. If this hydrogen right here is given to this water, that hydrochloric acid is the proton donor, okay? But that water accepted the hydrogen, so that's the proton acceptor. So in this case, the Bronsted-Lowry acid would be the HCl, but in this case also the Bronsted-Lowry base would be the water because it accepted a hydrogen. So that's a little bit different than the Arrhenius definition, but these are still two things that you need to kind of keep track of. So far, so good? Okay. All right. So what are some properties of a base? So bases will react to neutralized acids, and I'll show you that in a moment. And they had, I'm sorry, we did that just before. We talked about that just before, where they become like neutral with water. And then bases will change the color of acid-base indicators. I'll show you that in a minute. And then bases tend to feel slippery on your fingers, and they have a pH value greater than 7. So with a base, anything from like 7.1 up to 14 would be the pH range. And I say that bases tend to feel slippery, and they do. They tend to feel slippery. And the most common place in your life where you might have witnessed what a base might be would be something like soap. Okay, soap is is basically made of a basic substance. Now, some common bases. Most of your soaps at home are made up of some type have some hydrogen or sodium hydroxide in them. Baking soda that you might use to make the cookies, the chocolate chip cookies, delicious, right? Has sodium bicarbonate in it, which is basically baking soda. Antacids, the Tums for when you got that gurgly tummy and you take it and then you burp a lot and you feel a little bit better. You know what I'm talking about? Maybe? No? Okay, that's sodium carbonate. That's also a base. And then ammonia is found in many cleaning agents. One of the most common cleaning agents that would have ammonia in it would be the Windex, the forbidden. He was with me. Okay, yep. The forbidden blue juice under the kitchen sink. Windex. Yeah, right. Yeah, I usually clean my mirror also, but you don't want to drink it, but it's got ammonia in it. So let's talk about the idea of acid-base indicators for a second. So this situation right here is something that we call the universal indicator. The universal indicator will allow us to identify if an acid is present or if a base is present. Okay, and so in this instance right here, I started with sodium hydroxide earlier this morning, which was clear. Okay, sodium hydroxide, and then I added some universal indicator and it shifted to blue. Okay, and then I added some hydrochloric acid to it. Okay, and I shifted it from blue to like this pinkish orangish color. And so at this point, we're sort of pinkish, we're yellowish. So I'm going to try to shift it a little bit further. So what I'm going to do is I'm going to add some drops of the hydrochloric acid. And I'm going to mix that, my little mixy thing. And you see how it was sort of like that green color, but now it's sort of a reddish, purpley, well, not purpley, but it's sort of a reddish color. So I'm going to add some more. Try to get it a little bit more acidic. All right, so it looks something like that. Okay. So that's an example of an acid changing an acid-base indicator. So now I'm going to add some base, some sodium hydroxide, and I'm going to shift it to the basic side. So by doing this. Let's add some more. Oh, that's a good one. So now this is more basic than not, right? Because I've added a lot of base to it, and the indicator is basically telling me that it's that there's a base present. And the color of the indicator can tell me a lot about like how much base is actually present. So that's kind of important to understand about that. So that's an example of acid-base indicators changing in the presence of an acid or a base. All right, so now I need to talk a little bit about pH. Now, pH itself is the pH comes from a French phrase that's referred to as hydrogen powered. Okay, so it's referred to as hydrogen powered. So like the label on your note packet, you may have noticed was like following the hydrogen. And the reason why I put that on there is because a lot of what we do in acid and base calculations or in acid and base units is we're really, really tracking what's happening to the amount of hydrogen that's in solution. So the pH scale allows us to figure out how acidic or how alkalinic or alkaline a solution actually is. It's based, pH is a logarithmic scale. So like on your calculator, there might be this log button here that maybe you have used, maybe you've never used before, but at some point in your math class, you'll start using it. But it's based on what's called the base 10 calculation or base 10 value. So every log function has something to do with a quantity of 10 or quantity of 10. Now, acids tend to have a pH less than 7, and bases tend to have a pH greater than 7, and a neutral solution is somewhere around 7 exactly. So I'd like to take a second to talk about what that means in terms of pH and what's dissolved in the solution. So the next thing I want to talk about, or just take a second to talk about, is if I make a bracket like this, bless you, if I make a bracket like this, that means concentration. It also means molarity. Okay. So when we talked about something being like calculating the molarity of something in the last unit, we were really calculating the concentration or how much stuff was dissolved in that given value of water. Okay. So if I'm dealing with something that is acidic, the pH will be somewhere between 0 and 6.9. Okay. So that's an acid. But what that also tells me is that the H3O plus concentration is going to be greater than the OH minus concentration. What I mean by that is that I'm going to have more hydrogen in solution than I will have hydroxide in solution. If something is going to be considered neutral, that would tell me that the H3O plus concentration will be equal to the OH minus concentration. That means the amount of hydrogen that's present is the same as the amount of hydroxide that's present, which is why water is usually something that we refer to as being being neutral. If the pH is like 7.1 to 14, we're talking about being a base. And in this case here, the H3O plus concentration has to be less than the OH minus concentration. And so what that means is that when we look at something in terms of whether or not it's an acid or a base, what we're really looking at is how much hydrogen is present in relation to how much hydroxide is present. And I personally feel that this is a really important concept to kind of think about when we talk about something as being acidic or basic.
I was wondering if you have another sheet of this. No.
Not right now.
Oh, okay. Sorry.
I'm actually teaching.
Oh, sorry.
Yeah, no problem.
I thought.
All right, so anywho, here's an example of a pH scale, right? And the pH scale basically has a lot of things on it, but just like we talked about up above, if it's an acid, the pH goes down, okay? If it's a base, the pH goes up. And if it's neutral, the amount of hydrogen is equal to the amount of hydroxide. So things like batteries, battery acid, stomach acid, lemon, sodas, tomatoes, coffee, milk, those are considered to be acidic. Things like blood, egg white, stomach tablets like Tums, ammonia solutions like Windex, soap by itself, bleach, and Drano, those are considered to be basic. And the further away they are from 7, the more acidic or basic they are. So substances with a pH of less than 7 are considered acidic, and the closer they get to 0, the higher concentration of H3O plus they have. Okay. Now, so here's an example of that. So if I look at my pH of acids, right? Battery acid has a pH of 0. Okay, and that when you look at its hydrogen ion concentration, like right here, has a value of 1. Its OH minus concentration right here has a value of 1 times 10 to the minus 14. To put that in perspective, its decimal point, 13 zeros, 1. So it's 0.000000000001 OH concentration. If you look at the neutral substance up here, it has in hydrogen ion concentration of 1 times 10 to the minus 7 and a hydroxide ion concentration of 1 times 10 to the minus 7. So they're equal. So with your bases, again, the pH has to be greater than 7, and the closer the pH gets to 14, the higher the concentration of hydroxide will be. So here's my example here. Again, neutral. Hydrogen ion concentration is 1 times 10 to the minus 7. Hydroxide ion concentration is 1 times 10 to the minus 7. But with a base, right, the hydrogen ion concentration is 0.00000000000001, and the hydroxide ion concentration is 1. Okay? So what I'm getting at here is that the relationship between how basic or acidic they are is the relationship between how much hydroxide is dissolved or how much hydronium ion is present. And that basically sums up the properties of acids and bases and a little bit of background knowledge about pH.